All right. So two things. Uh, if you go to the website, the link was there for this, but obviously you're here, so you don't need that. But I also posted the review test for chapter 4. So you can start to review on that. And next Tuesday, we'll actually go over the review for chapter 4. So, and the next Thursday is the chapter 4 test. So that review is already up there, so you can print it out or just look at it and do the problems. I should have the answer sheet up there for it tomorrow. I didn't get a chance to do the answer sheet for it yet. So, but I should be able to do that for tomorrow. So that'll be up there as well. Tonight, we're going to look at the last thing, word problems, where you actually use this stuff. So the first thing to go over is just a basic overview on how to regularly do normal word problems. So whenever you're doing an application style problem or any kind of problem, always try to figure out what the problem's asking you, what you need to do. Drawing pictures is always very helpful. And what I try to do, how do you get sound to work? Check. So if you go to where the mic is on Zoom, there should be an audio setting to pick the speaker. No problem. So, and you could pick whichever one it has, and there's a test button there to test to see how to. Oh. And you can't hear me because I'm talking to you. The wonders of Zoom. There. So one of the problems that we're going to look at, like this would be a great example of a diagram. So just drawing it out, putting some numbers on there, trying to figure out what you're looking for. So whenever you're looking at a word problem, that's always very helpful. Don't always sit there and try to do the variables and stuff first. Sometimes just trying numbers to see how it works makes a lot more sense and actually helps you understand the problem a little bit better. That's why step 2 is to draw the diagram. And then step 3 is to actually introduce some variables to it. When you pick your variables, pick things that make sense for the problem. So I like the book likes always use Y's and X's. I typically never use Y's and X's. I'll use, like if we're talking about chairs and tables, I'll use C and T, or cupcakes and donuts, C and D. Like use something that makes sense for the problem. So if we're doing area, length and width, L and W, height for H, area for A. So don't use necessarily, you don't have to use the X's and Y's. Use something that makes sense for the problem so you can actually then look back and say, oh, this is why that's the case. So then we want to express that information in some way that we can actually start solving it. Once you solve it, or once you have that in there, we can start doing some of the applications of it. Always, so when we were looking at domain restrictions, we talked about the main domain restrictions. If you divide by 0, take an even root of a number, logarithms have that domain restriction. But one of the big domain restrictions that most people don't ever really think about is an actual like reality word domain restriction. So if we're talking about area can't be negative. So your domain restriction starts at 0. Or if we're talking about height can't be negative. So you're going to want your height to be from 0 on. So things like that are actually just as important when we're looking at these problems, because once we make the expression, it's going to work on the normal domain that that expression will work on. But we might want to restrict it down for closer than that. And then for what we're looking at tonight, we're going to look at optimization. So we're going to really be looking at looking for absolute minimums and absolute maximums. So we're going to look for critical numbers, and then we're going to do the first derivative test to figure out where the mins and maxes are. And then we could do the second derivative test, or we could just use when it's increasing and decreasing and things like that to figure out if it's a minimum or a maximum. All right. Let's look at some. So we had this problem, and this was actually the problem of that image that I just posted up there a minute ago. So this is what they're looking for. They have 2,400 feet of fence. So here's a couple different examples of ways that we could do this problem. So we have 100 by 2,200, 700 by 1,000, or 1,000 by 400. All those equals 2,400 feet of fence. So some of these problems you might have seen in the past, and you can solve them in different ways. Like this one, we can solve by looking for the vertex of a parabola. However, some of them look similar, but there's slight differences to them. And the power of calculus allows us to do any type of problem, which is kind of nice. So like this one, you might have seen this one as like you got fence, you have to build a pen, and you say, oh, it's going to be a square. Squares work well if you have all four sides. But when you're putting it on like a river or a house or a barn where you have one side that's not using it, it doesn't always work out to be a perfect square. So now that we got this, let's make some variables for it. Maybe. Okay. So we're obviously looking for perimeter when we have this. So we have two times the width. So we have, because we have the up on those, plus the length equals 2,400. And he wants the largest area possible. So area is length times width. So notice I'm not using X's and Y's. The book actually does use X's and Y's for this one. I'm using L's and W's for length and width. So now that we've got our two equations, we need to get it to 1. So we're going to solve this one for L because that's the easiest one to solve. It doesn't make a difference. You could have solved it for W and done it that way. It's just easier to solve for L. So now my area is W times 2,400 minus 2W. So that's my equation. So the next thing we have to look at, what's my domain restriction? What's the smallest width I can have? And what's the biggest width I can have? So the smallest width I could have would be 0. And the biggest width I could have would be half of the length. Excuse me. Oh, half of the width, which is 1,200. Half of the actual fence, which was 2,400. So that's going to be my domain for this problem. You are more than welcome to type questions, or if you have questions, you can just unmute and ask. Every way you'd like. I can see them both. All right, so we've got our equation. We've got our domain restrictions. Now we want to find our critical numbers. So there's my area. So the derivative of that would be 2400 minus 4W. And again, my restrictions are 0 to W to 1200. Give me 1 minute. I need a fast water. All right. So how do I find my critical numbers now that I have my domain? Correct. You want it to equal nothing. So 0 equals 2400 minus 4W, 100. So W equals 600. So now the question is that a minimum or a maximum? So if we look at this question, when is it less than that? So W is, when W is less than 600, my derivative is less than 0, so negative. So that would be the other direction, is greater than 0, so it's positive. So that means it's going down. Oh, sorry, I have that backwards actually. So when area was greater than 0, positive. So it's going increasing to that point and decreasing after that point, so that's a max. So my width is going to be 600. So now if I go back to my problem, if my width is 600, my length has to be 1200. And then if I multiply those two together, my area is 720,000 feet squared. So we can see how, like, this was one of them that when you were in pre-calc or even algebra 2 and stuff, when you did problems like this, you'd graph it and figure out the vertex, or you'd find the vertex algebraically. It's the same thing. We're looking for it in this case. The reason why calculus makes our lives a little bit easier is when you were doing that stuff in algebra 2 or pre-calc, you were only doing it to polynomial functions. So you'd be doing it to parabolas mostly. You might have added in some cubics there when you were doing for volume and stuff like that, but that'd be about as much as you'd be able to do. Now that we can look at, in the calculus side of it, we can find the derivatives and find the critical numbers. I can do it to any type of function to be able to find minimums and maximums. So one of the things that we can now start to look at is how to minimize the cost of objects for manufacturing and other things. So this is one of the problems that's actually done quite often. when anybody's manufacturing something, they want to be able to hold the most possible material inside of it, but have the least amount of material to make it. So you actually see this at the movie theaters when they're looking at popcorn, except they're doing the opposite direction. They want the actual shape to look as big as possible and hold as little popcorn as possible. So, but they still want the materials to be cheap, so they don't have to pay a lot of money for the materials. So you can start to look at how they actually use this type of stuff to figure out how to minimize costs and maximize materials, like those type of things. So this question is asking how we can use what we want a cylindrical can to be able to hold 1 liter of oil. And we want the dimensions to be the least possible amount of metal used. So if we're looking at the metal to be used, that's going to be the outside of the can. So we need surface area. This is one I would totally expect you to look up. The questions on the actual test are similar. Like I just changed some numbers in it. So if you need a formula for one of the ones on the review test, write that formula in your next card because you're probably going to need it on the test. So surface area is a can, 2 pi r squared plus 2 pi rh. So this is the top and the bottom. And that's the sides. Okay. So now, so now we need,
Hello.
we're looking for volume. So my volume for a can is pi r squared times height. And my 1 liter of oil is 1,000 cubic centimeters. Because we're going to do the sides of the can, everything else in centimeters, not in liters. So I need to convert it to make them be the same. All right, so now what we need to look at is we need to put these equations together so that we only have one variable that I'm dealing with. So let's solve this one for h, because h is basically by itself. So we have 1,000 divided by pi r squared equals h. And now I can plug that back into this problem. So 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. So I can now reduce this to 2 pi r squared plus 2,000 divided by r squared. Oh, sorry, not r squared, r.
Oh, okay, okay.
I caught it before you caught me. All right, so now that we've got our equation, we have to find the derivative of it. So notice I just moved the r up top. So this way, because then I don't have to deal with the division for my derivative. So a prime, so we have 4 pi r minus 2,000 r squared. And for all this, I totally didn't put this in there, but obviously my radius has to be greater than 0 for all this. All right. So we now want to find my critical numbers. So if I plug in 0 for this, I need to solve this for 0. So somehow, the only way to be able to solve this for 0 is I kind of got to get this to be one fraction. So if I fix this fraction, I can get my common denominator to be r squared. I have 4 pi r to the third minus 2000. Because I just multiplied that by r squared. So I've got that equals 0. So I can r squared ever be 0? Well, yes, it could be if r was 0, but remember, my radius has to be bigger than 0. So therefore, r can't be 0. So, but r could also not be negative or anything else like that. So I don't really have to worry about that piece. I can just look at the top. 4 pi r to the third equals 2000. R to the third equals 500 divided by pi. So r equals the cubed root of 500 over pi. So I've got my derivative and my radius now. What's up?
Wait, hold on. So pi r, and then how did you get rid of r squared from the denominator?
Because remember, if I'm trying to get it equal to 0, the bottom can never be 0.
Okay.
So really, I'm only looking at the top that I have to worry about that in this case.
Okay. Okay. Thank you.
No problem. All right, so now we've got to figure out when it's positive and negative to see where it goes up to that point. So this side's the positive. So it's greater than 0, and this side's the negative. Now, in both these cases, r squared is going to be positive. So the bottom doesn't matter, and it's not going to affect my problem. So 4 pi to the third minus 2000 is greater than 0. And since I'm not actually dividing or multiplying by a negative in this case, nothing's going to actually change from what I did before. So if r is greater than the cube root of 500 over pi, my slope is negative. If r is less than the square root of 500 over pi, my derivative is negative. So that means my slope is negative. So that means that r equals 3/500 over pi. That right there is a minimum. And that's because it's positive after it and negative before it. So it's going down into that point and up out of that point. So my radius has got to be that. And now I've got to find my height. So The height was 1000 over pi r squared. So we plug in the r. So the 2/3 power. So this simplifies down to 500 over pi. So the easiest way to do this, if you're trying to figure out how to simplify this down, is I basically need to make everything to go into the third inside the root. So if we look at this, we can do 1000 to the third cubed root over pi to the third cubed root. And then we have 500 squared over pi squared to the cubed root. So this way, everything's now under the cubed root. So, and then we can simplify this down to the 2 cubed root of 500 over pi. So that's my height. So that would minimize, that's going to give you a can that's going to hold exactly 1 liter of the fluid. That's funny, Scott. So that's going to give me exactly 1 liter of the oil in the can. And in essence, if we look at it, the height is exactly 2 times the radius. So if my radius changed, the height would change. It would hold more oil, but it would still minimize the amount of materials in it. All right. Any questions on these? I don't think, like, from what we did the other day when we were looking at the curve sketching, I don't think this stuff's much more complicated. It's just actually trying to apply it to a problem. And the hardest part of this one isn't going to be the calculus again. It's going to be coming up with the equations. Like that, in essence, ends up being the most complicated part. Is what's the equations that I'm going to use for it. There. Hi, Matt.
Howdy.
I've only gone over a couple word problems. I still got a few more to go. So, all right, a couple more that we're going to do. The next one is looking for a point that is close. So we're looking on in this case, a parabola, and we want to find the point that's closest to a different point. So the question is what are we going to use? What's the equation that I'm going to use to determine something that's close to something? What am I trying to minimize in this situation?
Is it the distance formula?
Yeah, we're trying to minimize distance. So my distance formula was that's my distance formula. So we've got a 0.14, and we don't really need to worry about the other x value in there. So I can change my distance formula into this to make it a little easier. So x minus 1 squared plus y minus 4 squared. All right, so I've got that. Now the next thing we want to do is, again, we only want to have one variable in the problem. So I've got y squared equals 2x. So let's solve this for x. So I've got y squared divided by 2 is x. So now I can change this. So I only have one variable. Y squared over 2 minus 1 squared plus y minus 4. So there's my equation. All right, so again, we're looking to minimize this. So we're looking for, again, the critical number. So we've got y squared over 2. So we've got this function, and the way it is right now, it's really messy. So what I can do, instead of having to worry about minimizing this whole thing, minimizing the actual inside of this is the same thing as minimizing the square root. Because if this number inside here is the smallest, then the square root's going to be the smallest. Does that make sense? Because in essence, what I'm going to do is I'm going to minimize the squared instead of the original problem. Just because this way I don't have to deal with the square root when I'm doing my derivatives. And I don't have to do multiple chain rules inside of each other. So now let's find the derivative of this. So we do have to do the chain rule. So the derivative of the inside of here is actually just y. And then it's 2 times y squared over 2 minus 1. Plus, that's actually just 1 times 2y minus 4. So I have 2y times y squared over 2 minus 1 plus 2y minus 4. Y to the third minus 2y plus 2y minus 8 is y to the third minus 8. So, yes.
How come aren't there any y primes?
Because, okay. Because in this problem, y is just like x. I don't have multiple variables, I only have one. So I'm actually doing the derivative in terms of y.
Okay, thank you.
No problem. All right, so now that we've got my derivative, y to the third minus 8, I need to find my critical numbers. So I'm just going to set this equal to 0. So y to the third equals 8. So y equals 2. So we also can look at when it's positive, when it's negative. So again, you can look at these. So the only time your sign is going to change is if you multiply or divide by a negative. So if you're looking at this is the positive side. I'm not going to multiply or divide by a negative. So y is greater than 2. So this is the positive side. And then when y is less than 2, that's when y3 minus 8 was less than 0. So that's the negative side. So that means it's decreasing to that point and increasing after that point. So 2 is a minimum. So my point, because again, we're looking for the point in this case. So I've got my y, I now have to find my x. So if you remember, the original problem was y squared equals 2x. So if 4 equals 2x, 2 equals x. So my closest point is 2, 2. Now, as crazy as this sounds, what we just basically did by looking at finding a parabolic curve, getting closest to a point. That is all NASA does with when they send probes to places. It's doing a parabolic or an elliptical curve around something, which if you're looking at one side ends up being almost parabolic. And you're wanting to know the closest pass to that point in space. So yes, their formulas are a little more complicated than this, but that's actually where this type of stuff is used. It's we're looking at something orbiting it and where it's the closest pass to the object that it's orbiting. So that's where that stuff comes in.
Can you please stay on that slide for like a minute or so?
Yeah, sure.
Thank you.
No problem.
I had a question on the previous slide because it seems to me that like the distance just kind of like escaped, or it was distance squared, but then it just changed to like f prime of y.
Yeah, I'll go back and I'll explain why in a second. I just used it so I didn't have to worry about the d squared. Yes, you always start with 0 when finding critical numbers. Because so the entire point of a critical number for the first derivative is to figure out where the slope is 0. That's where the slope is going to change direction. So that's going to be your minimums or maximums on your original problem.
So, I mean, I got the minimum. Why is it a minimum? Because it goes down then up. But
Correct.
why is it? Oh, you graphed it and then you look at the point of 0?
Oh, where did I get the 2, 2?
Okay, no, I got that part. It's just why is it minimum? Because I know you substitute it 2 into y. That's why you got the answer. I just don't know why is it minimum.
Oh, okay. So when you're looking at trying to find if it's a minimum, if the slope going into that point, so before that number, if the slope is negative, it's going down. And then after that point, it's going positive. So the slope's going up. So in this case, when my derivative, which is y to the third minus 8, is greater than 0, that's when it's positive, is when y is greater than 2. So after this point, my slope is positive. So that means it's going up. When y to the third minus 8 is less than 0, that's negative. And that's when y is going to be less than 2. So that means it's going down, negative going into it, or down going into it, and positive going out of it. That's why it's a minimum. If it's reversed, if it's positive going into the point and negative coming out, then it's going to be a maximum.
Wait, can you repeat that? I just don't get it.
Yes, I'm gonna actually, hold on. I'm gonna give you the exact test. So I'll go back
Yeah.
and I'll explain the other piece too. Cause I didn't forget about
Oh,
it.
but okay, you were doing first derivative test. Okay.
Yes.
You were doing first
Yeah.
derivative test.
Oh, I was doing. So I figured I'd just put that there.
Okay. You
All right. I'll go back to it in 1 second if you want to write it down. So all I literally did for the d squared is I just changed d squared to y or f of y, so I could just do the derivative, because I didn't want you guys to sit there and go, oh, I have to do the derivative of d squared, because you don't. I'm literally doing the derivative of this piece in here. That's all I'm looking at for the derivative is. So that's, I just changed it so there was something I could put the derivative on, and I didn't want to use a d, because I didn't want you to get confused with those two. Does that answer your question with the what happened to the d squared?
Yeah, well, I mean, I see that it's not there, but like, how does that not change the overall numbers in the end?
Okay, so if we're looking for, as crazy as it sounds, it doesn't. So when we're looking, because all we're looking for is when it's a minimum. So I don't really care. Like, I'm looking for when this value right there, the original the distance, is the smallest possible. So that if I do the squared, well, if you think about it this way, it's like this underneath here. If a number underneath the square root is the smallest, the square root of that's going to be the smallest. There's no way to make a number bigger in here that's going to give me a smaller square root out than that number. So that's why, in all honesty, I really just have to look at what's underneath the square root, and that's what I did with the d squared. I basically got rid of the square root, but I'm just looking at what's underneath the square root. It's not changing the end because I didn't use, I plugged the number in afterwards, so it's that 2 doesn't, it's still the y's. That makes sense? If I did it with the square, you'd actually get the same thing. It's just going to be really messy. I could if you really want me to. It's kind of funny. The book goes, you should just convince yourself that it works. That's literally what the book says. Because if we did the square root, we'd have to do it to the 1½ power, and we'd have to do the chain rule again, and it ends up canceling out the square root.
Yeah, it sort of makes sense. I understand.
Just trust me for the once. Rarely do I say that. In this case, just trust me. Well, do you still need this? Or are you good? All right. We are going to do a very simplistic economics problem. So, because the other place that this is used is actually in economics. When you're looking at profit margins and break-even points and those type of things, when you're looking to maximize revenue, it's like you want to look at how. So supply and demand says that as the price goes up, demand's going to go down, because that's typically what happens. Question is, you need to figure out what is the maximum price you can price something at that's going to sell the most, that's going to make you the most profit. That's what we're looking for. So because after that point, it's going to start going back down. So that's what we're basically looking at in this case. Like I said, simplistic case. So a store has been selling 200 TV monitors a week at $350. A market survey indicates that for each $10 of rebate offered to the buyers, the number of monitors sold will increase by 20. So if they sold it for $340, they would sell 220 of them. So did they make more money on that? That's what they want to find out, is how much should I cut off to make the most amount of profit, or in this case, the maximum revenue. So the first thing we want to look at is my price. So how much is I want to actually sell the item for? So my price. So it was $350. And it was for every $10 I cut off, it was 10. I don't figure out it. Okay. All right. That's where it is. Okay. So for every $10, we sell 20 TVs. So it's basically for every $1, we would sell 2 extra TVs. Because again, we're looking at we have to make this down to one specific value. So my initial price was $350. And we're subtracting the 1/2 time, and it's X minus 200. Because we're selling 200 monitors right away. So $450 minus 1/2 X is where I'm starting it. So
Where did 450 come from?
1/2 times 200 is 100.
Okay.
So really what we're looking for is we wanted to figure out the price for everything. So if I was to go the other direction, so if I was to up my price to $450, I would sell basically no TVs. Is where basically what that $450 is, because you'd go the opposite direction. For every $10 I increase, I would lose $20 or 20 sales a week.
What does X represent in this case?
The amount of the rebate.
Okay,
So it's every dollar you're losing. For every $2 you're taking, or actually, sorry, it's the amount of
X is
TVs.
number of rebates.
X is the number of TVs.
I can't hear you. It's kind of loud here.
Okay, so
X is rebate. Number of rebates, right?
no,
Can
X
you
is the
type in
number.
chat, please?
Sure.
Okay. Thank you.
No problem. X is the number of monitors sold. So if I wanted to, so in essence, what we're looking at is what do I have to price it at to sell that many monitors? So if I want to sell 100 monitors, I would price my thing at $400. Because 450 minus 1/2 times 100 would be $400. Is what they're trying. That's what the price equation's figuring out. It's like, what should I price? If I'm going to price it at this, that's how many monitors I'm selling. So now your revenue equation is just the number of monitors you sold times the price, and that's how much money you're going to bring in. So it's 400 x times 400 minus 1/2 x, or 450x minus 1/2 x squared. So this is the price, and this is the revenue. So now I want to maximize my revenue. So if we're trying to maximize revenue, we want to find the derivative of my revenue, and then we can look for my critical numbers. So my derivative is 450 minus x. So if we set that equal to 0, negative x equals negative 450. So x equals 450. So to make the most amount of money, I need to sell 450 TVs or monitors. Now, if we look at this, because you don't always necessarily have to do the first derivative test to try this out, you can just look at your original problem. That right there is a parabola, and it's opening down. So we know that's a maximum. So you don't have to necessarily do the first derivative test to do it. You can look at the information you have to figure that stuff out as well. So if that's how many monitors I'm going to sell, what do I got to price it at? So I'm going to put 450 minus 1/2, 450. So the price for sell 450 monitors, my price is going to be $225. So my rebate, which is what they were asking to figure out, is 350 minus 225, which is $125 off. So if I cut my price by $125, I'm actually going to make more money than I'm making now. Which is why every store out there has Black Friday sales and everything else, because believe it or not, they actually are making more money than they did before.
Where did 350 come from?
That was the original price of the TVs.
Oh, okay.
They're
okay.
originally selling it for $350.
Thank you.
No. All right. That's like I can do a million more word problems, but that's basically all you're doing. So I'm gonna do this. Quickly go over the quickly show you the review test. So this is the review test. So I've got 6 problems that are just I want you to find me the minimums and maximums, and then tell me which intervals they're concave up or concave down. On the actual test, you are only going to have to find one thing for them. So each one, it's you're either going to have to find me the minimum or maximum, or you're going to have to find me the interval. But I figured it's better to practice a little more than. Yeah, it was 450, not 480. Sorry, Scott. Hold on. It was the way I wrote it, I think. Yeah, that's 450. It just kind of connected as I wrote it. So practice those 6 problems, finding both of them. And like I said, each one's going to only have one thing that you're going to find. So there'll probably be 3 of them that you're going to find concavity and 3 that you're going to find the mins and maxes. You have 2 L'Hopital's rules. Notice how I wrote if needed. So check to make sure you can't do it a different way before you do L'Hopital's rule. And then we have 2 word problems and optimization problems like we did tonight. So the actual problems on the test are going to be exactly like this. I just changed the numbers in the 2 word problems. So it won't be very complicated to go through and do. So like this one, a box with a square base open, you need the surface area formula for a rectangular prism. So that's what you're going to need for that. I think all I did was actually just change this number on the actual test. So, all right. Any questions about anything? Tuesday's class will be basically the review of this test. So if you're good on this test, after I put up the answer sheet this weekend, I don't necessarily need to see you on Tuesday. The test will be next Friday or next Thursday. And then I will see you after Thanksgiving break, and we'll work on the beginnings of integration for chapter 5.
The review test will be on your website, correct?
It is already there.
Okay, thank you.
So it's right here at the bottom of this message right here.
Have a good day.
You too. You can always bother me. It doesn't bother me. As of today, I no longer am teaching during the day, so you can always bother me. Is this?